So yeah, thank you all for the really interesting talks. So first, I'd like to talk about this aspect of how we design codes for distributed quantum error correction. So there's various existing code families that people are familiar with. So as we've heard a few times, the surface code that Google are very interested in, and a lot of other places as well, and then more kind of exotic QLDPC codes that aren't as well studied and need more complex hardware but have lots of nice properties as well, and various other codes. How can we think about translating those codes over to a distributed setting, and what kind of design principles do we need to be thinking about when thinking about designing codes specifically for the distributed setting? So yeah, first, Coral, would you like to comment?
Yeah, absolutely. So within a distributed setting, you have, depending on your modality, there's a potential mismatch in gate rates and connectivity locally and non-locally. You've got local connectivity, which may be planar or may be fully connected, and you've got global connectivity, which is fully connected but is sparser. And so you need, and depending on how you're doing that, your bridge between that local and global connectivity, we have a saying. It might be around the edges, or it might be an area scaling thing where you're able to bring links out of the center. And general QLDPC codes with weight 6 connectivity, if they're long range, then you're going to need to be able to bring those long range links out at a rate that sort of scales with the area, the volume of the QPU, which is a little more challenging to sort of conceptualize in many ways than something that is locally planar, where you're very safe to assume you can just bring stuff out around the edges. Equally, sort of long-range check weights. If it's relatively high weight, it's much harder to perform those in a really rapid way, really flexible way. So I think that's definitely the start.
Yeah. Any other comments on translating codes over to distributed settings?
So yeah, so basically when you design codes, I think the most important aspect to consider, like in the future, you will have like multiple code blocks that run at the same time. And you want to do like perform logical operation with different code blocks. And the keyword is you want to do it like fault tolerantly. Basically like whatever interblock connection that perform between two different code blocks doesn't incur more errors than it should be. So ideally, like it is well known, like transversal implementation of gates are fault tolerance, but it is difficult to find codes that all the generator of the logical operators can be implemented transversally. This is difficult. We just like in our ship's code, we take the inspiration from classical error corrections. Maybe the answer is somewhere in classical codes because like we use classical simplex codes that basically has existed in the literature for like probably around 70 years. This code has this like beautiful characteristic. It has like so many automorphisms. Basically, it translates into depth 1 logical operator for arbitrary Clifford. And everything can be performed transversely. So this fits nicely if you want to implement like interblock logic, like fault tolerantly. But yeah, again, like if you see the code rate, because you want a lot of symmetry in your codes, your code rate sometimes doesn't look as good as if you design like very optimized just based on the distance. So again, this is like a delicate balance, like how much you want to sacrifice your encoding rate, but the benefit that you get back is like more like compact, more efficient logics. So yeah, there are factors that we have to consider when designing codes for distributed system.
Mm-hmm. Cool. Yeah, it's interesting. You're taking the inspiration from the classical error correction there. Any other comments on the kind of codes for distributed settings? Yeah.
I'd say that's definitely one interesting thing is whether it's tiled or non-local. And tiling means you're significantly more modular, and things like decoding can be local to the tile, for example. And I think one of the things that's really interesting from a tile perspective is once you've hit that level where you can do sufficient error correction within a node, it's sort of internally testable. But there's I think there's an interesting design space where you're not getting to the distances you need locally, where non-local error correction can enable validation of sort of advanced error correction codes, high distance error correction codes that aren't feasible locally.
So yeah, kind of building on those ideas, we know that there's lots of different hardware modalities around at the moment. We've got superconducting, trap tiles, neutral atoms, photonic, and lots of others as well. I'm interested in what you think about kind of how the challenges and potential for different modalities fit with distributed quantum error correction. And also, we've heard this term code design come up a few times. So I'm interested in how you're thinking about how we co-design these modalities with distributed quantum error correction in the future as well. So we could start with Brandon on this.
Yeah, so I guess this is kind of what I'm pretty focused on, is figuring out ways of integrating these optical interconnects with qubits without sacrificing the quality of the individual quantum processing units. And I think that this is like really the key takeaway of my research is just like at some point you will probably have to sacrifice networking rate in order to just keep the quantum processing unit operating at high fidelity. And then I think that like error correction is a way of maybe getting this back, where the error correction can be more lenient for the networking side than it is for the for like utilizing these like high fidelity local gates. So I think I think there's going to be a lot of development in the networking parts of things. I think we haven't really even pushed into like what fidelities we can get. Like we've kind of written down these things that say that we can get rates of like a megahertz and like fidelities of 99.9. But even in like recent years, like some of this work demonstrating atom photon entanglement kind of has shown that like there's some things that we didn't even think about, and this is work that actually like NanoQD showed in their theory paper, showing that like the kick from the photon excitation actually will limit your fidelity to some extent, and trying to understand these things better will only come with time and like actually like improving these things. And maybe we'll reach a regime where like the fidelity of the remote entanglement's actually better than the fidelity of the local entangling gates, and then we'll have to like switch our way of thinking about these things. But I think it really does come with co-design and kind of like these two things developing together.
Cool. Yeah, interesting the comparison of how that might change over time as the hardware changes its properties as well.
It seems like I guess it feels like most qubit modalities, they need some sort of distributed system, right? Like the IBM example. I mean, I'm not a hardware expert, so I can't really comment on what the details of that were. But superconducting qubits, you cannot move them around in the same way as neutral atoms, but you cannot. There's only so many you can fit in a fridge, right? So there has to be some distribution there. The one qubit technology that is interesting and counter to this possibly are spin qubits, right? So things coming out from Australia, right? Their big selling point is they can fit it on one wafer, right? From silicon technology. Now they have real difficulties with say controlling 1 million qubits on one wafer. So that's a challenge, absolutely. Everybody has their challenges, right? That's one of the things that's absolutely true. But it feels like most of the qubit technologies are going to have to tackle this in some way. Saying as someone who's not a hardware expert.
Yeah. Coral, do you have any thoughts on this?
With I think logic operations are a really really huge part of the story for how to do it. Obviously, with it's all about the code automorphisms, and there's this huge design space of, as you say, targeting really high performing codes that recent work has found like rich sets of rich families of automorphisms in some very high distance, high rate codes. But they are very uncomfortable gate sets. They're not very orthogonal. They're not very complete, and they would be very difficult to compile to if you tried. So I think there is a sort of a co-design challenge there. Something we are interested in is the potential for switching, for being able to morph topology over time, and whether that can equally bring out some of these whether you can get any of these symmetries and flip through any of these symmetries with that switching fabric, which would obviously also be very fast.
Yeah, I agree. Like logic, like how you do logic with like codes in distributed like system should be like look a bit more closely, more seriously, because yeah, at the end, yeah, as I said, you will run multiple code blocks for running like meaningful algorithms, short algorithm, quantum chemistry units. Monolithic, I don't think will be the approach, but I'm happy if someone proves me wrong. But also, we need also to look at like each platform. What are their advantages? What are their disadvantages? And try to leverage the advantage to do your logical operation. If, like, for example, maybe like for some architecture, like doing lattice surgery actually like the best way possible for you to do logic, then do lattice surgery. You don't need to resort if like making non-local connectivity is like super difficult for your platform. Then, yeah, or it's like, as you said, like there are codes that have a huge automorphism, but like for some type of operators, it's like very uncomfortable to implement. Maybe it's a mixture of like transversal gates with lattice surgery, a mix between the two. That also can be the way. But I think at the end of the day, what we want to ask, like, yeah, because surface code like has been like studied for around 25 years now, so like running algorithm in surface code has been like optimized to the minuscule level. It's just like if we found new codes, I think, and QLTPC codes like specifically, it's just like people taken like more seriously just like this past 5 years. So there are a lot of open questions how to do like for this code, specific codes family, how to do like logic like properly. So yeah.
Just one comment. Just again, QLTPC, absolutely super beautiful. We should be exploring it. You say surface code has been massively optimized. Only just in the last month or so, Google just announced that they managed to reduce the number of qubits needed to factor 24/8 bit number from 20 million down to 1 million. And that came from optimizations in the surface code. So I think, like, to say it's all done in the surface code, I think that maybe it could be seen as a bit premature. But obviously, QLDPC is super exciting, and we should also be exploring that as well.
Yeah, so lots of room to innovate on all the codes,
Exactly,
hopefully.
Yeah, definitely.
Yeah, great. So now I'd like to shift a bit to a topic that came up in Neil and Daryus's talks, in particular of decoding. So I'm interested in the panel's comments on what moving to the distributed quantum error correction setting means for decoding and what we should be considering there. So Neil, would you like to start?
Yeah, like I said, one of the things I want to remind everyone of, two things, was decoding error correction is more than just about decoding. Also, interfaces are really important. So with a well-defined interface, I actually think the lovely thing is with a well-defined interface, I think the problem does not change that much, right? Which is really cool. I think that's a absolutely fantastic thing. So if you imagine that, like I said, on that interface, you have a control system, and that control system is telling the qubits and also these interconnects to do something, right? And what's coming out is some classical signal. Now, if you're distributing that the error correction scheme across different QPUs, there's going to be a signal coming out from different QPUs. That's cool. Just send that over that interface and let the error correction system work out how to put all that information together, right? And that is really like I think someone earlier was about standards. Our proposal there is a first go at what this standard would look like. Now, it will be wrong, right? And we'd love feedback on that, and we'd love input from the community, right? But essentially, in a distributed setting, I think the problem is essentially the same. Get the information across this interface, and the error correction will work out how to put it all together, how to window it, how to get the decoders to talk to each other, and what have you. So I think that's a lovely thing about this distributed system.
Yeah, cool.
So yeah, I agree, because probably like the best approach of doing like specifically decoding is like you will like you run multiple code blocks. Each code blocks will have their own dedicated decoders, and then between these decoders they kind of need to talk to each other, because like if once you have inter-block connections, then there is a correlation between two code blocks, and then you need like much more sophisticated, basically like how to make these multiple decoders that run in parallel basically communicate to each other, and the amount of data that need to be transported between these like decoder units in different nodes is actually massive if you consider the code that you will consider for running that utility scale. So yeah, for example, like as I said, like in our simulation in the paper, we have two code blocks, but we decode them as a single. There is only one decoder that decode these two code blocks together. But in practice, you will have, let's say, 100 code blocks, and you really cannot put one decoder to decode all of them, because one thing that we need to know, that decoder should not be the bottleneck of the entire thing. Like, as I said, the worst thing that you can do is like you optimize your qubits to perfection, but then you forget to optimize your decoder, and then your decoder become like your bottleneck of the entire system. And then basically you finish your algorithm, but it's waiting to be corrected. And then, yeah.
I should say also, Coral and I were having a great chat earlier on today. And one thing that actually came out of that conversation, so like I said, we have this interface, and we think we know what the information that should be sent across that. And then from this conversation with Coral earlier, we realized, oh, there might be another piece of information when you do distributed quantum error correction that we also have to include sending across this interface, right? So we're not saying we have it right. We're just that principle of sending the information we think is correct. But what that information is so we can work out what that is as we develop together, I think.
Exactly. Yeah. So one of the things we've this is below the QEC layer, but as part of the Bell state generation process, the Bell states are heralded within our detectors, but they are projected that they're actually located on qubits within partner QPUs, and sort of as such, in order to do this with high fidelity, with high rate, and without bottlenecking the quantum performance at all, you really need to be able to synchronize both our control electronics and the QPU control electronics to a CMOS limited degree of precision. So one of the things that we've been doing recently within the QDA is this partnership, this integration of White Rabbit and partnership with CERN to provide that open standard for scalable frequency and timing distribution that is that ground layer for being able to actuate operations between different control stacks at sort of CMOS limited precision, levels of timing precision, which is very extensible and should, equally bringing that out at rate and precision is what we need for decoding.
Cool. Yeah, good to hear that there's conversations happening from this meeting already, leading to new thoughts and ideas. Great. So I'd like to pause my questions and hear some from our audience. So please, if anyone has any questions for our panel on distributed quantum error correction, now's a good time. Yeah, Claire? We have a microphone coming. Yeah.
So a very naive question from me, which is, do you already have on a single machine like multiple decoders and you're managing sort of communication between multiple decoders?
Yeah. And just like give you, just to highlight, depending on, so we've talked about how you do logical operations, different qubit platforms do it in different ways, lattice surgery, transversal logic, there's other things you can do, these automorphisms. The information that needs to be transmitted between decoders varies depending on the type of operation that's happening underneath it, right? So like with lattice surgery, just think of it as a great big sea of qubits that isn't really moving, and you just break it up into windows, and there needs to be some reconciliation along the boundary of these windows, which is kind of what has to happen. With transversal logic, it's a little bit different. You kind of have transversal logic basically creates correlations that you don't see in the superconducting qubit types. And essentially different messages have to be passed between the decoders to actually take that into account. So yeah, it depends on how you do computation, but yeah, we're definitely focused on that. Yeah.
Any more questions from our audience? We have one over here. We'll just wait for the microphone. Thanks.
Hi, Jordan from IQ Capital. I'm interested in your thoughts on the role of machine learning for discovering and optimizing QEC. Thanks.
I mean, yeah, so I've got a few thoughts about that. So I think, so the machine learning, so, okay, machine learning is a very large term, right? The really interesting AI decoders are the ones that use the transformer model, which I believe underpins LLMs, right? So that's what Google and DeepMind have a really lovely paper. The work with NVIDIA and QERA have a nice piece of work there. The thing that's really interesting about that as a decoder is the amount of training data that you need, right? So in Google's paper there, they were getting a certain logical error rate, but as they increased the size of the system, the amount of training data they needed grew exponentially, and then the logical error rate tapered off, right? So how to train these decoders, I think, is a really, really interesting problem that needs to be solved. How to also window a large computation with these types of decoders, I don't think that's known either, right? There's another thing that I've sort of looked at recently, and this is more a bit of a hunch, backed up by a paper that recently came out that showed that the codes that IBM are proposing in their architecture, somebody threw a transformer decoder at that as well, and it performed worse than the sort of state-of-the-art algorithmic decoder, right? So, but the transformer decoder worked really, really well on surface code, right? Now, there's technical reasons which I can get into in conversations afterwards why I think that might be the case. I don't think it's a given that transformer-based decoders are going to be useful in QLDBC codes. That's still to be worked out and discovered, but I don't think it's a given. I think it's clear that they're performant with the surface code, and there's reasons why that would be the case. But with QLDBC codes, I think that needs to be worked out.
Cool. And did we? Oh, yeah.
Yeah, that also might be a naive question. Are there opportunities if you knew more about the distribution, the probability distribution of the errors? Particularly, I'm thinking in extreme cases like the Alice and Ball, where you have only, I forget, only bit flips, but no phase flips, or vice versa, to then come at it with more targeted codes than everything we've heard, because these are assuming, I assume, IID, sort of all kinds of error shapes and distributions. Are there opportunities to do better, like in redundancy factors and so on?
Yeah, so basically, any information about errors is a good information for error correction. So basically if you know which errors are more prevalent in your hardware, you should tailor your error correction to basically accommodate that type of error. Because for example, Alice and Bob, they only experience more, I think, phase flip. Correct me if I'm wrong, so there is no point of designing code with bit flip. So that's why you can increase the encoding rate significantly, because you only care about one type of error. Also, the distribution of error, because it is more related on the because when you do error correction, for example, with QLTPC codes, the information that you put into decoder is like how likely it is the errors like located, how likely it is that the error located on each location of your quantum circuits, and that's like a meaningful information. So basically, any information about your hardware, the characterization of a well-characterized device is like very good information, like informing for people who design quantum codes to like be more like efficiently design your error correction codes. Yeah.
Yeah, I think so the IID model, that's useful to sort of test out ideas, right? But again, if you look at Google, this is another place where actually machine learning comes in. So they use machine learning algorithms to essentially try and understand their noise better, and then you implant that onto the decoding algorithm that you have to run, right? So it's not thinking about IID at all, right? It's using machine learning to understand the correlations in the device and then translate that into the decoding problem. So there's like an initial step of like calibrating the decoder, you would say, right? And I think machine learning actually could play a really pivotal role in the whole computing architecture as that part as well. Yeah.
Great. So in our last few minutes, I'd just like to take an outlook towards the future of distributed quantum error correction. So I'd like to ask each of our panelists, kind of looking towards the next few years, in the next 2 or 3 years or beyond, what kind of milestones or demonstrations do you think might happen or are most interested in or excited about seeing towards distributed quantum error correction? So we can start with Brandon.
Yeah, so I guess what I'm hoping to see in the near future, I guess like the first like teleported CNOT was like a recent result that kind of just happened. I hope to see that scale up, and I think groups like some represented here are already working on these things. But one thing that I'm pretty interested in seeing is getting the rates just higher to the point where it does breach a threshold where it would even make sense to make more of these modules. And I think like in an academic lab, this is pretty challenging because it means it's like twice the cost of any experiment you'd want to do. And on top of that, it's like fairly risky. Like you could build like just a neutral atom quantum computer, or you could build like 2 and then add additional difficulty, and it has to all work. So I think maybe this will happen in like an industry setting first even. And then beyond that, I think once these CNOT gates are happening at a rate that's high enough, then like distributed computation will start to happen and show some effectiveness. And then I think the other thing that's interesting is really like at the hardware level, I think we don't really have a super great understanding. And I guess going off of the question that was just asked, we can also like bias errors in a way where maybe the error correcting tolerances can get higher. And if we know that like all of our teleported gates have a certain type of error, then maybe they can be even more lenient and I don't have to do as much networking.
Thanks. Daryus?
So yeah, 2 things. One, I think like probably like in the coming near term, like 2, 3, 4, 5 years, there will be more and more demonstration of logical qubits in small scale quantum research. So this will be like exciting time to do error correction because of like I study error correction, I study quantum error correction. It's just so exciting that the thing that you study now being implemented in real hardware. So yeah. So I think like as a community of quantum error correction, we are looking forward to this like more and more demonstration of logical qubit with like start with like small scale quantum codes. And the second is like I think like the last slide I told everyone how to annoy a quantum error correction researcher. Basically, if a quantum So basically, if a quantum error correction researcher proposes a new code, just ask those questions. Can you do logic with it? Is it efficient? Can you decode it? Yeah, So basically, like at the end of the day, as me, I'm working on the very top layer of the quantum stack. So what I care about, like give me a code, but also tell me if I run, let's say, SOR algorithm, everyone's favorite algorithm, what is the space-time volume that I need to run this algorithm? I don't care about like your raw encoding rate, but at the end of the day, I care how many qubits I need, how long it will take to run SOR algorithm with your code.
Thanks. Coral?
Yeah, I mean, I completely agree with both of these, but as a theorist, I'm really looking out towards the hardware, going, what's happening? And I think one of the things with all of today being about networking, being about ways of building these distributed systems and these scalable modular systems, the ball is definitely rolling. There is momentum towards building sort of tiled and modulars and perhaps scalable or extensible architectures. But I think that ball has started rolling. But what will sort of convince me that it is really really unstoppable is that first demonstration of a remote link in a system with also competitive local fidelities. When that exists, I think the first utility scale machines are very, very close.
Great. And Neil?
Yeah, I guess high level megaquark, right? That's why I think that's really, really, really important. Again, I will say it's one of the UK government missions, 2028. So I think it'd be great if, as a whole community, we try and strive towards that. A bit more seriously, I think meaningful logical operations. That's what I want to see. So logical operations where you have many rounds of syndrome extraction, and also, and I will confess that Riverlane is guilty of this as well. The word real time is thrown around an awful lot. Meaningful feedback, real time error correction, right? So where you are doing a computation where you actually, it's the outcome of a measurement determines whether or not you do what gate you do next, and you actually do that gate, right, and keep going. I think these sorts of demonstrations are they're coming, and it'd be super exciting when they happen.
Great. Well, thanks everyone for the very interesting comments. We're about to do a mic swap after this for the next session, but let's thank all of our panelists.